So let's keep difference frequency generation. Okay. And last time we Last time we briefly talked about the physics picture here. You have omega 3 high frequency input. Also, you input a little bit of omega 1, a lower frequency. And then what will happen is that this omega 1 will get amplified. And then there's idlers also generated at omega 2. Okay. The process is you have a photon of omega 3. It becomes 2 photons, one at omega 1, the other at omega 2. Okay. And then this seed photon of omega 1 is like working like a trigger, okay, to trigger more photon of omega 3 to decay into this 2. And last time I think we also talked about our prediction, right? If this is Z, assume phase matching, then okay, this power. Okay, we predict that the power of omega 1 photon and the power of omega 2, they will increase, okay? Because every time you trigger one more omega 1, it kind of accelerates this process instead of decelerating it. And this is called optical parametric amplifier. Now let's work on the math of this. And yeah, we just skip a lot of the the nonlinear equation. We've done this, a lot of times in this class. So let's just jump to this. And then we assume E3 is much larger than both E1 and E2. Okay, so E3 is acting like a pump. And because it's much larger, so when you transfer some energy to E1 and E2, you can in some way think E3 does not change much. Okay. So and also we assume phase matching condition. Okay, just to make our life easier. And I know about you guys, but we've do second harmonic generation and some frequency and now difference frequency. And every time, if you really want to make sure you're getting the correct result, every time it seems that you need to go through the very fundamental, you need to go through this general right, nonlinear equation. Right. Okay, it just seems that way. And then, well, first of all, it's true if you want all the parameters. Okay, if you want to derive all the parameters, yes, you have to go through this. There's no other way. But sometimes, like for example, we just want to know, does it grow, does it oscillate, this type of behavior. You don't care if there's a factor of 2 here, right? Sometimes, so do we still have to go through this every time? And the answer is actually no, especially if you're doing it in a quantum mechanical way. Okay, so let's just take all those as second harmonic generation, some frequency, different frequency generation as an example. And let's see what we can do here. Okay, so this process, what you will see is that you create 2 photons, one at omega 1, the other at omega 2, and you annihilate a photon from omega 3. Right? So if you think of them as particles, before this process, you have a photon at omega 3. After this process, it goes into 2 photons, one at omega 1, the other at omega 2. Okay? So let's see if we can do this without bringing up Hamiltonian. I think it's not possible. So okay, let's bring up Hamiltonian. You don't have to know very detailed, but because the rule actually, after you use it, you derive a rule for these equations, and then you can simply use those rules. Okay? So these transitions, okay, we know creating 2 photons, what they are, right? We have talked about this. Creation operator. Create a photon at this frequency, create a photon at that frequency. And you want this photon to disappear, so you have a annihilation operator. Okay. And now think about state. You label it as N1, N2, N3. Okay, photon number of omega 1, omega 2, and omega 3. Now you want to move from here to here. Then what you do? You first apply annihilation of at omega 3. So you reduce the photon number by 1, right? And then you create a photon at omega 2 and create another photon at omega 1. So after this operation, these states become, there's some normalization factor, but these states become this. Okay. Now the next part is, let's see how we can do this without.
Professor?
Yes.
Remember when you operate with the annihilation creation operators, it gives you a coefficient, a factor up front.
Yeah. Yes.
We're not considering that right now.
No.
Okay.
No. Yeah. So that coefficient actually goes into E.
Okay.
Right? Because the coefficient is square root of, let's say, N3. Square root N3 is just proportional to the amplitude of E3. Okay, so that's actually consistent. Okay. So what happened is, in your Hamiltonian that kind of the Hamiltonian decide how your system evolve. There's a term act like this. Okay, it's just a process. You just move this to here. There's a process saying annihilate of A3, create A1, A2, and then generate G1. Well, sorry, and then there's a coefficient, something similar to this. Okay, but it's just a coefficient. And then the next step you do, this one is a little bit probably too much for you guys, but you can actually write down, for example, I think there's an I here. This is a commute operator. So you can actually do this. Okay, this is usually called Schrodinger. The Heisenberg picture. Okay, and it might look complicated at the first sight, but think about how we calculate this, right? If you have A dagger, this is 1, right? If you have A1, A2, it's 0 because they're not related, right? So you can actually use this for calculation. Let's see. So what this can do is that every time you can now imagine what will happen if you think, yes, this is correct. Okay, A. So when you do this, it's A1 is not relevant to A2 and A3. They're just coefficient for A1. Okay. Yes.
So Hamiltonian is supposed to be Hermitian, so you also need the.
Yeah. That's right. Because there's a separate process, right?
Yeah.
Like a reverse process. Yes.
Okay.
Yeah. So this is just for deriving the form of this equation.
Okay.
Yeah. So when you do this calculation, the only thing that matters is A1 with A1 dagger. And then you know the result is the number. Right? So what will happen if you do this calculation? It becomes A1 dt proportional to that's a little weird. Let me see. Oh, that's actually correct. Okay. Okay. Right. You do this A1 here, and then it comes out as a number. And then the A2, A3, they don't interact with A1. You just keep them here. Now you get a dynamic equation, dA1 dt proportional to a coefficient A2 dagger A3. And of course, you can write down the conjugate form here. And then you will find actually you have another one, and then you can construct them into E. But usually, when you look at this, you can say, OK, now this is a quantum regime. Okay, as E is simply A plus A dagger, right? We know this, A plus A dagger. So what this would mean is that this quantum equation goes into dt coefficient might be a different one, okay? And then E2, so E3 first. Okay. So it's just by writing down how the interaction happens, you can actually derive the equation without actually doing any calculation. Okay, and actually an easier way to do this, once you believe in this, okay, you have to do one time to believe it. And then what usually happens is, let's say for example, let's say some frequency, okay. So what will happen is, if you need to know 3 is coming from 1 and 2. You just write it down like this. Now how about, let's say, E2 here. E2 here comes from a E3 minus a E1, right? Minus this one, creation of this one, annihilation of this one equals this one, right? So this is a minus. So annihilation in quantum mechanics, we know that it's conjugate, right? So E2 is, you need a E3 and then conjugate of E1. So this is a rule. When you know how the process happens on a photon level, you can simply write them down, very straightforwardly. Okay. Now the question is, what's a coefficient, right? It doesn't matter for example, it doesn't matter the absolute amplitude of these two. But the question you want to ask is, are they equal to each other? Right? Because when you try to solve it, this actually matters. Right? When they two times together, do they have a I sign? Do they not have an I sign? Do they have the same sign or opposite sign? Right? This actually matters. So the best way to solve this is to normalize. Well, the best way to solve it is to think about the conservation law here. Okay. The number of photons created in omega 1 equals to the amount of photon you destroy in omega 3. So the coefficient of omega 3 disappearing must be the same as omega 1 being created, right? The other thing is, when a photon of omega 1 is created, another photon of omega 2 must be created. So they must have the same coefficient. Okay. So to get this coefficient, the first thing you need to do is you normalize E3 to something usually we call A3. It's normalized to the photon number. What you can do is you divide it by h bar omega 3, and then there's another coefficient, okay, related to, it depends on where you start from, okay, if you start from here, no, okay. So you start from P3, the power of your photon, okay, divided by 3, give you the number of photon per unit time, right? And then P3 has a link to, I think it's C, n3, there's a factor. Okay. So then what will happen is you now know, well, these are just, all these are constant. You only care about n, right? Because n is different for different wave. Okay. So what you get is n3 E3 square omega 3 goes to something we call the field normalized to photon number. Okay. So you can say A3 equals to N3 omega 3 E3. Okay. I don't know if you guys noticed previously in the some frequency generation, there's actually a coefficient like this showing up in your final result. I think it's n1 omega 1 times either omega 2 n2, something like this. So this show up because it's a requirement of photon number conservation. Okay. So here, what you can do is, now you know E3 equals to A3 divided by this. So you can write down equation now. Okay. Because this is photon, so this coefficient must be equal to each other. Okay, photon number conserved. And then you plug A3 back. A3, well, A1, you just change N3 to N1, omega 3 to omega 1. And then you get a coefficient. Right? You get a coefficient that is N3, N1. So, for example, this one, you will get G naught, okay, you have N3, omega 3, omega 1 divided by N3, N1, and then A2, right? A2, and then N3 come, let's see. And 3, 1, omega 3, omega 1, and then A3, it's on the opposite side. So you have omega 3 come up, omega 1 come up, omega 2 come up here, and 2, and then you give a square root. And then you write down E3, E1. But normally, I think people are good with this, okay? Because you can calculate how the photon number change, and then use this to directly get your power, because power is the thing you measure, right? It's not the field energy. Okay? So a lot of time people start with here, and then the other thing is whether there's an I here. Oh, it's actually I here. Okay, so this one you just need to do it once, and then you will find there's a complex. There's an I coefficient here, if my memory is correct. Okay. So So for you guys, I think this is a very helpful check, right? When you write down something like this, you can check if your result makes sense or not by looking at this. Especially, for example, when you calculate something, if your result shows up as this, then you know there's something wrong, right? Because it doesn't agree with the photon generation process. And then you can easily add back like this. Okay. And this actually becomes, more useful when you're in we call four-wave mixing. Okay, process called four-wave mixing. You have two input and then two output. And then the interesting thing is that when you have more than two input, that's what happened in our real research. Our research, we have five different channels for the photon. They are each at different frequency, okay? And then they are all as input, and then all output. So what will happen is that, like, these two can mix and generate two. These two can also mix. So there's a lot of combination, okay? If you're being a very well, we do it a mathematical way and then expand this thing. It's doable, but like a better way to do it is simply say, okay, you have, let's say you have EI here. Right? You must create it from two photons. And then you annihilate another photon. And then you have omega I plus omega L equals to omega K plus omega J. And that's it. And there's a universal coefficient here. That's the same for everyone, if you use this as normalized to photon number. Okay, so for this three-wave, it might seem, well, why am I going through this trouble, right? But when the number of waves increase, and that will happen, in real experiment, especially for pulse, then you gain a huge advantage, okay, by using this photon, probably a photon method, I would call it. Okay, now let's come back to here. Last time we briefly mentioned how to solve this. It's just the same old thing here. Okay, you take the first equation, you do a derivative of the first equation. What this would do is generate a derivative for E2. And then the derivative of E2 is shown here. Okay, so by plugging in, you can get the final result. So let's just do this really quick. We neglect the coefficient first by the I here. Okay, K1. Let's put it up, capital K. And then E3. And then plug in this one, okay? I, K1, E3. You need to take conjugate on this. You get minus I K2, right? And then E1. Okay, so I is -1, so this is a plus sign. Okay, so you get K1, K2, E3. The definition of K1, K2 here might be different from the one I have in the note, but it really doesn't matter that much. And then you now end up with okay. Just to mention that the so-called coefficient I mentioned here is contained in the wave vector K1 and K2. Okay, the wave vector has refractive index, and wave vector will also cancel out one of this. Okay, this will cancel out this, so you are left with something similar to this. Okay. Okay, so we can put it as right. This is a positive number, so we assign gamma square as the coefficient. So this is the equation for difference frequency generation, and when compared with some frequency, there's only missing a minus sign here. Okay, I think we briefly talked about this last time. And the solution for this is, straightforward. Everyone should know this. Well, the solution, the general solution for this is E plus minus gamma Z. Right? You take derivative twice, and then the gamma plus minus gamma will come out. And then no matter if you're plus sign, minus sign, because it's square, it always show up as gamma square. Okay, so you can assume the general solution is a linear combination between these two, plus sign and minus sign. So you have A1 okay, and the same for E2, because it doesn't matter which one. Well, you do derivative of this one, and you get this equation. Okay, if you do derivative of this one, you get the equation for E2, and then the coefficient is simply the multiplication of these two. So both E1 and E2, they share the same gamma. The other way to think about it is whenever you generate a E1, you generate E2. So the coefficient must be the same. Okay. Okay. So this solution is, when you look at this, it's actually not as easy as previous one, right? Because previously, sine 0 is 0, cosine 0 is 1. This one, both of them are 1 at z0. Okay, so sometimes people use your combination kind of as a try to make it look similar to sine and cosine, right? So people sometimes do this. Right? Sometimes people do this because if you write it in this form, now you know, for example, for E2, the coefficient in front of cosine must be 0, right? Because it's 1 as z equals 0. This one, as z equals 0, is 0. Okay, so it's just a different way to do linear combination. Okay, so depending on which one you're more comfortable about. Personally, I like this more for no reason. Okay. Now let's do the boundary condition to figure out this coefficient. The boundary condition is, the input, right? And then the input is there's a field of E1, you know what it is, and E2 is 0. Okay. If both of them are 0, then what will happen for this equation? For example, let's say both of them are 0. Then what's the solution to this equation? Just look at here. You don't need to solve anything right there. So this term becomes 0 at position 0. This term is also 0 at position 0. Right? So you now get at position 0 there E1 and E2 are 0. Their derivatives are also 0. So it's like they stay 0 for the rest of their time. Okay, that's a classical. That's also a check for your solution. Okay, so that's a classical case. And then in quantum case, as we talked many times, there's always half a photon there. So it's never really 0. Okay. Okay, so for this one, E2, it's easier because there's a 0 here. We now know A2 plus E2 equals 0. So E2 is a sign, right? Because A2 and B2 have a minus sign. Okay. And then you also know A1 plus B1 equals E1. Okay. And the second thing we know is that this is the first boundary condition, and the second one, just like before, we have the derivative, right, at z equals 0. E1, because E2 is 0, so the derivative of E1 is 0. Okay, and what this means is derivative of this one, derivative of this one. Okay, so A1 equals A2. A1 equals B1. So we actually solve A1 and B1. Gives to A1 equals B1 equals half E1 0. Okay. And now next is this one, the derivative of E2. This one is a little bit complicated because you kind of have to use this. So let's see how we can do it. I, and this coefficient I think we call it K2, and then there's a E3 0, E1 0. Okay. Right, okay. That's from this equation. And this equals to derivative of this one is A2 gamma minus B2 gamma, right, at 0 point. So let's do this one. We know A2, B2 are off by a minus sign. Okay. So here you have 2 A2 equals to I K2 E3. Okay. E1 star divided by gamma, and gamma squared is this. Okay, so probably we can just write it back. Pi 2 omega 2 squared K2 E3 okay, divided by gamma. Gamma is divided by, okay, divided by gamma. Gamma is square root of this, including E3. Okay, so it's mu naught S. It's weird why K2 disappeared. Chi2. Okay, let's just keep going. Okay. Guess I'm not sure if I made a mistake here because it's weird that the end result is irrelevant to Chi2. Non-linear coefficient. That's really weird. So I'm not so sure about this, but I also couldn't spot where I made the mistake. Okay. So let's just keep going. So cancel all this. Okay. And then have omega 3, omega 2 squared, omega 1, omega 2, and then you have K1, K2, K. Omega 2, omega 2. So omega 2, omega 1. And then K1, K2. So it's K1, K2. Okay. And then this one only gives you, this is a really odd result. Okay. Give you a phase. And then you have E1. Oh, okay, I see why. Okay, yeah, that's fine. So this coefficient doesn't have chi2, and it also doesn't have E3. That might seem odd, at the first sight, because you guess that this coefficient should be larger, right, with your input or with your chi2. But the chi2 and E3 are really contributing as a gain. Okay, gamma here. Gamma have chi2 and E3. Okay, so the rate you grow depends on your input and your nonlinear coefficient. So there's nothing wrong with this coefficient being independent from chi2 and from your nonlinear coefficient and your input. So this is fine. Okay. Yeah, if you check the dimension, these two cancel each other. These two cancel each other. Dimension is the electrical field, right? And then you can take one further step, as K1 is N1 omega 1 divided by C. So this one actually goes to omega 2, omega 2. There's omega 2 here. Okay. K1 is here. So there's N1 here. Okay. And then omega 1 with this. Okay. And then E I phi 3. Okay, so this is your result. Okay, and something we can do here is that this is your system. You can, assign a time 0, right, to make one of the phase, either E1, E2, or E3, as z equals 0, 0. Right? You can make a phase. You can choose a time to make a phase 0. So here, you can, well, there are two suggestions. One is to choose E3, so you don't have to carry this phase term, right? You can get it to 0. The other one is you can also, choose E1, so you don't have to carry this conjugate. Okay, it depends on, which one is easier for you. In the calculation, they all give you the same result. Because when you change this one to 0, equivalently, you change the phase of E1. So the conjugate would, give you the result. Okay, so now we have E1Z equals to A1 equals B1, so it's okay. E2Z is okay, we're choosing E1 as a frame. Okay. Yes, B2 equals minus A2. So by looking at this result, one thing you notice that actually we don't have to go through this. We don't have to go through this step to calculate the A2 because there's a photon number conservation here. Okay, you can directly get this coefficient. By assuming if one E1 is generated, there must be another E2 generated. Okay, so that's why you see omega and n. That's the same as omega is associated with your photon energy, n is associated with your power. In your power, there's n here, right? We all know this number of photon p divided by this is okay. That's why it's omega 2 divided by n2 and n1 divided by omega 1. Okay. And of course, if you don't do this calculation, then you will never know there's a phase term here. Okay. You might know there's a phase, but you don't know what the phase is. Okay. So now we know the solution. And what it looks like. It looks like the first thing is if you start to grow, okay, really quickly, this term actually goes to 0, right? So it's at first it might have some balance, but eventually it will look like exponential growth until you hit the point that you're comparable to E3 and then E3 drop. And when E3 drop, then your your gamma will drop. That will slow you down. Okay, but until then you're fine. This is P1. Okay, and then the other one is P2, right? P2 start from here And then in my let's see. So first of all, the power of E2 can surpass the power of E1, right? Because if your frequency of E2 is higher than E1, right, then you're generating the same amount of photon, but each photon you have more energy, right? So it's possible you can go like this, or you can go like this, okay? It's all possible, okay? An important thing to operate this amplifier is something we assume at the very beginning is the phase matching condition. Okay. This is, we say we want phase matching condition, and what this means is N3 equals to N1 plus N2. Okay. So so what happened in your experiment is that, well, if you're lucky enough, once you input this 2, you can see a little bit of signal here. Okay, if you don't, then you're in big trouble. Okay, because you don't know. Well, let's say if you do see a little bit of signal here, okay, very weak signal, and then it depends on the crystal you use. You either tune the angle or you use some temperature tuning, depending on your system. But what you do, for example, if you turn the temperature up a little bit, if you see decrease, then you know you're operating at the wrong side. Then you now decrease the temperature, and then you see it, coming up. And then you keep doing that until you hit the limit. Okay. And then if you have 2 parameters to control, then you better do the calculation to see whether you have a local maximum, right? Because, for example, if your angle and temperature together, then your efficiency might look like this is a 2D map. So temperature, angle, and then so more dot means better. More dot means higher power. But thing is, there could be 2. One is, the real maximum, the global maximum. Some could be the local maximum. Okay, so you can be trapped here. And so the way to avoid this situation to happen is really to get the crystal parameter and do the calculation. Okay, assume phase mismatch, and then see if there's a local maximum. And this actually happens quite a lot, even with very simple system. Let's say couple light from a laser into a fiber. Right? There's usually there's 5 knobs. Usually there's 4 knobs, right? Fiber here. This is your. Let's say this is your laser. Well, could do better than this. Okay. Okay. Let's say you have a laser beam, and you want to couple into a fiber, right? There are actually at least 4 knobs. Actually, 5 knobs. Yeah, that's right. You have this direction, this direction, and then X, Y, Z, right? 3 of them. Why this direction matters? Because the beam is not parallel, right? It has a profile, and you need to match the profile of your fiber. So that's 3 knobs, okay? And the other 2 knobs are tilting of your laser beam, okay? For example, this one, you might not have perfect match, so this one might look like this, okay? Then you need to tilt. Okay, so there are 2 directions you can tilt, okay? So for this case, in theory, you might not get local maximum, right? But in reality, since these are not perfect, if you get a bad copy of your laser, you could be trapped in a local maximum. And then usually the solution is to just spend a lot of time in it, okay? Or you call technical support to, say this is a big trouble. Okay. The parametric amplifier nowadays is actually used quite a lot. And first one is used to amplify short pulses, right? Because this effect, because you only use a virtual energy state of your atom. So it's actually really quick. You doesn't need to wait for the relaxation of your atom. Okay, so this one, at least to my knowledge, maybe the state of art really evolved, but to my knowledge, you can amplify pulses around 60 femtosecond width. Okay, 60 femtosecond. That number might not make a lot of sense to you guys because you never work with femtosecond, this unit, this dimension. So let's see what femtosecond is. Okay, 6 times 10 to the minus 14 second. Okay, still doesn't make much sense. Now let's times it with speed of light. So how wide is the pulse? Okay, how wide is the pulse? Okay, roughly 20. So 2. Okay, the beam, if you take a snapshot, okay, freeze everything, the pulse will look like it has a width of 20 micron. Okay, that might not seem very small, but think about it, the wavelength of a light is usually about 1 micron, right? So what happened inside this wave is there's only 20 oscillation of light inside, because each wavelength, let's say it's 1 micron, then you only have 20 wavelengths inside. Okay, so that's actually fairly amazing. Okay, and so to do this amplification, okay, so what people found is that you have to build a parametric amplifier that is broadband. You guys know the Fourier transform, right, between time and frequency. Okay, if you're very short in time, then you're very broad in frequency. So, for example, I don't remember this very well, but I think if you have t omega 2 pi, right? T is the pulse width, omega is the bandwidth. Okay, so first of all, your pulse looks like this, and then your frequency domain will look like this. Okay, you have a broad band. Let's use delta. Okay, delta omega 2 pi t is 60 femtosecond. 6, 10 to the 4th. Okay, these two roughly cancel each other. This is not right. It's either 1 or this. Sorry, I forgot the coefficient here. Okay. To my memory is somewhere around 10 terahertz. Okay. So probably the 2 pi is here, or you simply don't have 2 pi, just 1. This 2 pi coefficient will give you like 36 times difference. So I apologize, I forgot which one it is. Okay, but from our experiment, we actually we can generate pulses around 100 femtosecond width from a chip-based device, very small. And then in frequency domain, they look like this, 10 terahertz wide. So if you want to amplify it, you have to have your parametric gain very broadband. Otherwise, what will happen is if you have a narrow band, if the pulse is this broadband, okay, and then your amplification is only like this, then only the overlap part is being amplified. It's like adding a filter to a frequency domain. Okay, so so this is something quite important. And then the other thing why people use parametric amplifier, one is, well, they're fast. It can be made broadband, for some material. The other thing is you can actually tune this. You can tune the phase matching condition, right, by using either angle or your either angle or your temperature. Okay, so you can do, for example, if you want. Oh yeah, the other thing I forgot to mention. Yep, sorry about this. So one is you can tune, so you can amplify the pulse here. Probably you can also amplify the pulse here if you tune the condition. Okay. The second thing is that you're generating a second pulse, P2. So suppose your pulse generation is limited to some area. Okay? You cannot go any further. You can use this optical parametric amplifier to do a difference frequency and then make the second one here. Okay, and then this can actually go really far away, right? Because as long as you can satisfy the phase matching condition, it's different than some frequency. Some frequency is, let's say, omega 1 plus omega 2. You can only double the maximum, right, of your frequency. So some difference frequency, it can be, in theory, arbitrarily small, right? They can be like 10 hertz difference, 10 terahertz difference, 100 terahertz difference. Then the end result is, let's think about it. If you're off by 100 terahertz, that gives you roughly 2 micron. That's a wavelength associated with 100 terahertz. I think this one, sorry, 3 micron. Okay, and then if you now tune a little bit, So the frequency difference is 10 terahertz. You can do that, right? Just by moving these two pulses, moving these two, the pump and your laser. And this actually gives you, 30 micron. And these are very, very different wavelength range. For example, below 3 micron, well, wavelength longer than 3 micron, usually you don't have a very efficient laser diode. Okay, you have to use quantum cascaded laser. And then here, I think the quantum cascaded laser, or correct me if you guys have used it, some quantum cascaded laser has to operate in low temperature, and that's probably a problem. Okay, and also once you have a laser diode, the frequency is fixed because you are using a real transition, so you cannot widely tune the laser diode. So this one, okay, and then it's very, very recent. People use difference frequency generation. A group in NIST, they do, I think I mentioned this before, I think it's 4 micron all the way to 20 micron using one crystal and one laser. Okay? So cover this entire band. And yep, if you guys are interested, you can Google for this paper. Okay? And that's all for today. On Wednesday, we'll talk about optical parametric oscillator. Okay, and if you guys want to sign up for a presentation, send me an email or just talk to me in person. Okay.